Welcome to day 6, word problems. We've been doing word problems throughout this unit, but I really want to focus on them today. They're a big part of what I want to do in this unit. They're going to be a big part of your test later this week. So let's write an equation. We have Vulcan, population's 4, growing, so I better do 1 plus, let's see, I got to change this to 0.075. V equals 4, 1.075 raised to the x. Romulus, that is decreasing, so I better do 1 minus 0.05. I get r equals 8.95 raised to the x. And what do I want to do with these two equations? I'm going to set them equal to each other. 1.075 to the x is equal to 8.95 to the x. And remember, when we solve, I want to isolate b raised to the x is equal to some number. I'm going to get all the exponential part on one side. So what I'm going to do, I'm going to divide by 4, I'm going to divide by 4, I'm going to divide by 0.95x, I'm going to divide by 0.95x, and when I rewrite this, these cancel, I have 1.075 over 0.95, parentheses, both are being raised to the x, is equal to 2. Now what I can do is log both sides, and this x jumps up in front. And I got to log this side, and to solve all this, I need to divide by log of this ugly fraction. Notice how I just write everything out, because at the very end I'm going to let the calculator do all the hard work for me. So all I'm going to do right now is type this into the calculator. So I'm going to type in log of 2 divided by, don't forget close your parentheses, log of 1.075, don't close your parentheses here, divided by 0.95, close your parentheses, and you get that result. Just to show you how consistent things are, I could have done ln of 2 divided by ln of 1.075 divided by 0.95, and I would have got the same result. Log or ln, it doesn't really matter. So like I said, I typed all this in the calculator, and I got about a little bit more than 5.5 years that Vulcan will overtake Romulus in population. Okay, let's look at the next one. This one I got to be careful. I got to make sure I read the words correctly. I have an initial population of this increasing at a continuous rate. Continuous means e to the rt. I have to use 0.032. So I have my population is equal to 10,000 e to the 0.032 t, because it is increasing positive. I want to know how long it takes to triple. So triple the initial would be 30,000 equals 10,000 e to 0.3032 t. I'm going to divide by 10,000. I really have 3 is equal to e to the 0.032 t. To me, I could have done this to begin with. I could have done this problem to begin with, because what did I really want? I wanted triple. So the initial population is irrelevant. I don't care if the population was 10,000 or 100 or 2. Triple is triple. Well, I'm going to rewrite this problem over here. E to the 0.032 t is equal to 3 triple. I'm going to ln both sides of it, because when I have an e, I want to natural log it. 0.032 t is equal to ln of 3. Divide by 0.032. I get t is equal to the ln of 3 divided by 0.032. And I'm going to put this in the calculator. ln of 3, close parentheses, divided by 0.032. And I get a little bit more than 33 years. I can minimize this. Bring this up. 34.332 years is what I get. So pH is the measure of how much hydrogen ions are in a solution. It's given by this formula. The negative log of the hydrogen concentration. Okay, so water, pure water, is pH is 7. So if I want to know how much hydrogen is in pure water, 7 is equal to the negative log of my hydrogen. Well, to get rid of the negative side, I do negative 7 is equal to log of my hydrogen. This is base 10. I'm going to curl it. So my hydrogen concentration in water is equal to 10 to the negative 7th. Okay. Lemon juice has a pH of 2.3. So for lemon juice, I have 2.3 is equal to negative log of my hydrogen. Again, I can make it negative. This is base 10. I can curl it. So for lemon juice, my hydrogen concentration is 10 to the negative 2.3. Okay, so not as many. Or it's actually more. So the idea is that I want to figure out how they compare to each other. So I want to set up a ratio. I always want to put the higher number on top. So lemon juice is actually the higher number than water. So I do 10 to the negative 2.3 over 10 to the negative 7. And I subtract logs, I get 10 to the 4.7 is my result. Well, I put that in the calculator, and I get it's about 50,000 times more. So lemon juice has 50,000 times more hydrogen ions than pure water. But another way we could have done this is to subtract pH values. So I could have done 7 minus 2.3 was equal to 4.7. And because pH is a log, I could have done 10 to the 4.7, and I would have got the same result. So for this next one, I could subtract my logs, or I could use the whole ammonia is 12.3 negative log of my hydrogen. Make it negative. Curl it. And the hydrogen concentration in ammonia is 10 to the negative 12.3. I could do my ratio. This time I want the water on top because it's the higher concentration. I get 10 to the negative 7 over 10 to the negative 12.3. And I get 10 to the 5.3, which is about a little bit less than 200,000 times. So water has 200,000 times more hydrogen ions than ammonia, or by subtracting logs, subtracting pHs, I could have done 12.3 minus 7, you get 5.3, and I could have done 10 to the 5.3, and I get my number about 200,000. That's the way pH values work. Well, let's look at our population. So on January 1st, 2000, there was about 6 billion people growing at this, so I had to do 1 plus 0.0138. So my population is 1.0138 raised to the x. I want to see how long it takes to get to 7 billion, so I do 1.0138 to the x is equal to 7 billion. I divide it by 6. I get 1.0138 raised to the x is equal to 7 over 6. And I get what I wanted. I get my exponential isolated, and I log both sides. The x goes in front, so x goes in front, and then I divide by the log of 1.0138, and I get x equals log of the fraction 7 over 6, over log of that percent, 1.0138. And I'll put this in the calculator and see how long it takes to reach 7 billion. Okay, I'm going to type this in the calculator because I let the calculator do all the hard work for me. Log of 7 over 6, then divided by log of that decimal. See, this is all the hard work. I don't have to figure all these out. I don't have to do it in pieces. And I get there and it's 11.25 years. So it was 11.25 years, but I didn't say in how many years. I want to know when. That means I want the actual calendar year. So the initial year was 2000. So I have to add 2000 to this, and it's actually the year 2011. About 1/4 of the way through the year, but sometime in 2011 we hit 7 billion people. The next question is, when does it double? Well, I don't need the initial population. I don't have to use this 6. I could just do 1.0138 raised to the x is equal to 2. Is that what doubles mean? If you want to set that equal to 12 and then divide by 6 to get 2, that's fine, but I think it's just a waste of time. I'm going to log both sides. X moves in front. I'm going to divide by that log of 1.0138. So I get x equals log of 2 over log of 1.0138. I'm going to put this in the calculator, and let's see what the calculator says about that. And I'm going to cheat here a little bit because I don't feel like typing it all out again. I'm going to do 2. I'm going to do 2 over 1. Yeah, with that 2 over 1 is the same thing. I get 50.6 years. So I get 50.6 years. Again, I got to add 2000 to that. So according to my calendar, it is the year 2050. Oof. Hopefully I make it to 2050. We'll see. And the last one basically says, when we expect our food shortages to be at 50 billion. So I'm going to take my equation, 6, 1.0138 raised to the x is equal to 50. I'm going to do exactly what I did for part A, but I'm not going to write it all out because I already did it. I know x is going to equal log of 50 over 6 over log of 1.0138. I'm going to put parentheses, but this is what I did from part A. Right here is going to be exactly the same, except instead of having 7, I'm replacing it with 50. I'm going to put this into my calculator, and I'm going to cheat a little bit. 50, oops, 50 slash second insert 6, and there we go. I have it all. I got 154.7 years. So 154.7 years, and I got to add 2,000 to it, plus 2,000, and the actual calendar year I get the year 2154. I'm not making that, and I don't think any of you are going to make that time either. So we don't have to worry about running out of food in our lifetime. Okay, you guys have all heard about earthquakes are measured by the Richter scale, and the Richter scale is actually a log scale. It's based on logarithms. So the E is the energy created by that seismic wave, how much in kilowatt hours. So I remember in 1989, I was watching the World Series, and there right before the game started, right before Game 3 started, I believe, there was an earthquake of 7.1 on the Richter scale. Pretty big. It did a lot of damage. So how much energy was there created? Well, I'm going to do 7.1 is equal to 0.67 log E minus 1.17. I'm going to add this to the other side. 8.27 is equal to 0.67 log E. I'm going to divide by 0.67, divide by 0.67. I have 8.27 over 0.67. I don't even care what that is equal to log of E. I know this is the base 10. I'm going to curl it. I'm going to curl it back. And my energy is equal to 10 raised to the 8.27 divided by 0.67. I'm going to put that in the calculator and see how many kilowatt hours I get to do this. So on the calculator, I'm going to clear this all out. I could do my second log key because that gives me my 10 raised to 8.27 divided by 0.67. I get 2.204. See this? E to the 12th means 10 raised to the 12th. 2.204 times 10 to the 12th kilowatt hours. That's a whole lot of energy. So in 1906, San Francisco had a giant earthquake of 8.6 on the Richter scale. Giant. So how many more times intense is this? Well, the difference between 8.6 and 7.1 is 1.5. It wasn't 1.5 times as strong. It's a lot stronger than that. So what I need to do is do my 8.6 is equal to 0.67 log of E minus 1.17. And according to what I did in the other problem, I add the 1.17 divided by 0.67. I get E is equal to 10 raised to the 9.67 divided by well, that'd be nice if I could do math correctly. 9.77 divided by 0.67. I put this in the calculator. I get 3.820 times 10 to the 14th kilowatt hours. So now I'm going to do my ratio of the higher number, the 1906 earthquake, over the 1989 earthquake. So 3.82 times 10 to the 14th over 2.204 times 10 to the 12th. And I get it's about 173.3 times as strong. So just think about this. If you had a 1 pound weight fall on your toe or a 173 pound weight fall on your toe, that would be the difference in magnitude. If you want to use the difference in logs, another way you could have done, you could have subtract logs, subtract the Richter scale, and divide by 0.67, and I would have had 8.6 minus 7.1, which is 1.5, divided by 0.67, and I could have done 10 raised to the 1.5 over the 0.67, and you would have got the same number. I'll show that on the calculator. Calculator, clear this out. 3.82 to the 14th divided by 2.204 12th. I get that number, or I could have done 10 raised to the 1.5 divided by 0.67. And look, I really got basically the same number. Oops. And let me see if I can find my thing. And okay, so here's a formula that takes the idea of a group of people trying to memorize some words and what is their retention after so many hours after they first learned the words. So X is input the hours, and the F value, the Y value is the percent. So after 5 hours, only 20% know this. I'm going to plug those numbers in. So I have 0.20 is equal to 1 minus k, because I don't know what k is, ln of 5 plus 1 when I plug in my x of 5. I'm going to subtract 1. I get negative 0.8 is equal to negative k times ln of 6. I'm going to divide by negative ln of 6, divide by negative ln of 6. And I get k is equal to, according to my calculator, so I type this into the calculator, I get k is equal to 0.446. So my general equation for this memory is 1 minus 0.446 ln of x plus 1 is the equation for, I guess, this specific list of words. So after 1 hour, I have 1 minus 0.446 ln of 1 plus 1 is 2. I put that in the calculator and I get 0.691, or 69.1% of the people will remember the list of words after 1 hour. Then it says, when will no one be able to remember? No one is when y is equal to 0. So I do 0 equals 1 minus 0.446 ln of x plus 1. Remember, I'm solving for x. Subtract the 1. Divide by that number. And I get, I'm just going to leave it as that ugly little fraction with a decimal, is ln of x plus 1. Now remember, ln has an e in it, so it becomes x plus 1 is equal to e to the 1 over 0.446. I'm going to subtract 1. So at the end I have x equals e to the 1 over 0.446. I have no idea what that is. That's what the calculator is for, minus 1. I put that in the calculator. I get 8.414 hours later. I expect that no one will remember any words from that list. Okay, so I have no idea what 10 raised to the 3.4343 is without a calculator. I have no idea. But I do know that 10 to the third is equal to 1,000, and 10 to the fourth is equal to 10,000. So 10 to the 3.4343 is somewhere in between 1,000 and 10,000, which means it must be a 4-digit number. It's got no choice. It is a 4-digit number. So let's go to my calculator, and what is 10 raised to the 3.4343? Let's put that in the calculator, and let's see what we get. Second, 3.4343. Oops. 3.4343. And there's my number. 2718.316. Now to me, the significance is, what are the first 4 digits? 2718. And if you go back to what you learned in grade school, 10 raised to the 3.4343 is about equal to 2.718 times 10 to the third. So 10 to the third is a 4-digit number. So let's keep that mentality. Now I could type these in the calculator, some of them. I can't type them all in the calculator. 10 raised to this, well, look at this. That 0.4343 is significant. I go to the calculator. Oops. Second, 10, 9.4343. Look at that. I get those same numbers in the exact same order, except now this is a 10-digit number instead of a 4-digit number. So this really is 2.718 times 10 to the 9th. It's a 10-digit number. This one is going to be exactly the same. I'm going to 10 raised to the 20.4343. And look at that. I get exactly what I had before, those digits, except I have raised to the 20th, 2.718 times 10 to the 20th. And this last one is going to be 2.718 times 10 to the 100th. Notice 3, 10 to the 3rd, 4-digit number, 9, 20, 100, 100. But I cannot put this in the calculator. 100.4343. It says overflow. It means this is too big for the calculator. So just because it was too big for the calculator doesn't mean I can't do it. The significant part of this problem was every single time I had a 0.4343. That's what gave that 2.718. So for this one, I'm going to type this in the calculator. Log of 2 raised to the 216,091. I get that overflow error again because it's too big. It's way too big for the calculator. So I need another way. And this is what I'm going to do. I'm going to pause. So here's my other way. I'm going to use my rules of logarithms. And I remember my rules of logarithms says this guy can go up front. And so this really is equal to 216,091 times the log of 2. And that will work out for me, and I'm going to get a nice decimal number for that. So there I am. I had the one above was an error, but this one I can type in the calculator is just 216,091 times log of 2. I get a nice decimal number for it. So I have my log of this 2 raised to the 216,091 is a 65,000 number. So if I really want to know what is 2 raised to the 216,091, by my rules of logarithms, I could do 10 raised to the 65,049.87279. Okay? They're going to be about equivalent. But remember, 3 was a 4-digit number, 9 was a 10-digit number, so on and so forth. So this must be a number that has 65,050 digits. I'm not going to write that out. But how do I figure out what I should get? Well, I'm going to use the decimal part. So if I do 10 raised to the 0.87279, I put that in the calculator, I'm going to get I'm going to get kind of like the beginning of the number, like I had 10 raised to the 0.4343 was at 2.718. So here I did the decimal part, 10 raised to that. So I get a nice easy number that I can work with, at 7.46. So the 7.46 is key. So 2 raised to the 216,091 is about equal to 10 raised to the 65,049.87279, which is about equal to 7.46 times 10 to the 65,049. Okay? And that would be a number that has 65,050 digits.